Hello, today we will talk about factor analysis. We will introduce orthogonal factor model, we'll mention its assumptions, then one method of estimation, just the method of principal components, and then we will solve a couple of exercises. But let's first see what actually is the factor analysis. Well, we can say that it has the same objectives as principal components analysis. So we kind of want to find the true dimension of data. So we want to reduce the dimension and to somehow interpret those new variables that we get. So even though it's similar to PCA and it has same objectives, it's different. It's not the same. PCA tries to explain the variance structure of the data, but factor analysis is concerned with explaining more than just the variance. So it takes covariance structure of data as well. In that way, you can consider factor analysis as some kind of extension of PCA. So we are somehow finding a way to approximate the covariance matrix sigma of our vector x, random vector. However, we are here trying to use some variables, random variables, that are actually not observable. And those random variables we call factors. So consider, for example, this model. It is in matrix form. Let's go here. So this one is not in matrix form. Those variables f1, f2 to fm are not observable. In what sense? For example, when we had regression models, we actually had random variables that were observable instead of those. So you can say that it's kind of similar, but the assumptions are different from the regression model. So they differ a lot, those models. Let's see first what is what in this model. So we have here a random vector, so that is x, that has p components. Okay, that vector has mean mu and covariance matrix sigma. So the sigma is what we are trying to interpret, to approximate. And what we assume here is that x linearly depends on those unobservable random variables. So those random variables, f1 to fm, are our factors, or we call them common factors as well. Those are the errors, so our random variables. Okay, in linear regression model, we assume that they are normally distributed with constant variance. Here we do not need that assumption. Usually m is smaller than p, because our goal is the dimension reduction, and those L. So for example, L21 is the loading on second variable and first our F, so our factor. Or that loading we can say weight in some sense. So weight of the second variable on our first factor. So this would be loading of our second variable on our mth factor. So notice that errors are unobservable as well, not only our f1 to fm. So here we have m plus p random variables that are unobservable and only p quantities, so x1 to xp. So without some assumptions, we cannot verify that model. We don't know the actual covariance structure for this orthogonal factor model. So we would need to make some assumptions in order to do that. So say that we have that random vector x, f that is unobservable, and usually it's strictly smaller. It has no effect if it's p. And this is our matrix, so matrix of factor loadings. That's how we call it. So our assumption is that expected value of f and e is 0, so E is our matrix, actually a vector, not a matrix, where the covariance of our unobservable random variable, so this one, this is a vector. It is just you have 1 on diagonal and 0 otherwise, but m times m matrix. Okay, so this index says that this is identity matrix m times m. And the covariance of our errors we will denote with sub c, and on diagonal it has elements c1 to cp, or depending on notation it can be c1 to cp, it does not matter the notation. So just on diagonal it has those elements, and otherwise it's 0. And also they are independent, which means that the covariance between our E and F is 0. So now it is a matrix P times M. Okay, so now using those assumptions, it is actually easy to prove that the covariance of X is equal to this expression. But in order to prove this, you would need to assume that the model is linear in F. So you cannot have in the model, for example, here f1 times f2 or f1 squared or similar. So this is another important assumption. But we do not need to prove this, so let's just work from here. So we have that covariance of our vector x is equal to LL transpose plus ARP C. From here, when you write this in this matrix form, so when you multiply and add these values, you can notice that the variance is actually sum of these loadings, squared loadings, plus the specific variance. So it's just, on the diagonal, we have here variances, and when you just multiply those matrices, and this is a diagonal matrix, so it has only on diagonal the specific variances, so we call those CIs or CIs, specific variances. So we know that the variance of xi is equal to this sum plus the specific variance. So we can see that we have that the variance is sum of two things, communality, okay, and the specific variance. So the communality is actually the portion of the variance, of this variance, of the it variable, contributed by those m factors. And the specific variance is the other portion. So the portion that contributes to the specific factor I. So this is for the diagonal elements of covariance of X, and also we have others, so covariance between xi and xj, so xi and xj, and it is just given by this sum. And the covariance of xi and fj can be proven to be fij, or you can say that covariance between x and f, okay, is actually the loadings matrix L, so this matrix. So we actually know one method to reproduce this covariance matrix in this form. So if we take that actually M is equal to P, we have the orthogonal decomposition that we already used. So we know how to take this matrix L. So it would be a vector of our square root of our eigenvalues and eigenvectors. So from our spectral decomposition, the vectors are orthogonal, E1, E, and EJ, so the eigenvectors. And in this case, this psi is going to be actually zero matrix, because it is the exact composition of our covariance. So this is sigma. It would be equal to this lambda L times L transposed. So it is actually L is given by this. So you can see by this expression. So L transpose is actually our sigma by choosing this vector as L. Okay, so let's go to the method of principal components. If we have ordered eigenvalues and eigenvectors, then we can write it like this. But as we have p and we want m less than p, so for the dimension reduction, then we will choose less eigenvectors and less eigenvalues, okay, and make another decomposition of covariance matrix. The choice of M in this case is similar to the principal components. So we would choose them similar way. We would look at the eigenvalues and decide. There are also some others like rule of thumbs or similar, but we'll not talk about it. This is like introduction to factor analysis, like only the basics. We will also mention that there are other methods of estimation like method of maximum likelihood or regression, etc. And note that we write lambda 1 hat when we have the sample covariance matrix and eigenvalues and eigenvectors with hat. It means that they're taken from the sample covariance matrix instead of this population covariance matrix. And we estimate the psi, so psi tilde, only by subtracting S from L tilde transpose. So basically this expression here is our estimation of our psi. And then we have a matrix of residuals. Okay, let's move to the exercises, Excel. So while listening to the lecture, open the PDF. There we have given the covariance matrix of a random vector. We are given that we need to check if it's generated by this factor model. In this factor model, we only have F1 unobservable, so it looks like it's standardized, and we have loadings matrix L. So 0.9 is in the first F1, then 0.7 and 0.5. So those are our loadings on each variable, and where we assume that everything is satisfied, the assumptions. So those three things are given. So psi, okay, L, we can read it from the model, and our covariance matrix. What we need to check if sigma is equal to this one. So L transpose plus psi. When we check, when we do the calculations, okay, we already have done this multiple times, so I will not explain how to do it, but we can see that it actually reproduces the covariance matrix very well. So our covariance matrix can be approximated using this model. Next, what we need to compute is the cumulatives and covariances between zi's and f1, because now we have only one factor. So we can go to the PDF just to see what are the cumulatives. Okay, so we can see here. Let's find it. So the covariances are just the loadings on I yacht, okay, and the cumulatives are the sum of the squared loadings. But here we have only one loading, right? So what we need is just squared one. So 0.9 squared is our first, for the first Z1. Then squared 0.7 and squared 0.5. So those are our cumulatives. And covariances between our unobservable f1, our factor, and our zi's. So z1, what we said, it's only that single loading between the variable and the unknown factor. So only L1, 1. So this is this, L1, 1, L2, 2, and L3, 3. This is the simplest model with only one underlying factor. So this was simple. Okay, so this is just for you to get intuition as we talked about it earlier. We will not do anything complicated. Let's see another one where we are given, so this is our sample, covariance matrix S, so it is given. So now we assume that we want two-factor model. Okay, so for some prior knowledge, we know that we need only two factors underlying, so only two common factors, F1 and F2. So assuming that, and assuming that we have our covariance matrix, we want to use our principal components method. Let's quickly see what we need here. So for our principal method, components method, we need our eigenvalues, right, of our sample covariance matrix, and we need our eigenvectors. Okay, we already know that our m is equal to 2 by assumption, and then we can compute our L tilde, which is given by this. Then we can compute our psi's, or specific variances, and in the end, the residuals. Okay, so let's see how will that look like. Okay, so eigenvalues and eigenvectors, or our sample covariance matrix, can be computed in R, in this case. And what we get ordered are the sample, the eigenvalues, and our eigenvectors. Okay, so we said that we will have hat notation when we take off the sample covariance matrix instead of the population covariance matrix. And those are our vectors in columns. So we can easily now apply the formula for our L tilde, so our square root of lambda 1 times E1. So we can just write it easy because we use only two. So it is two-factor model. So our m, let's go back maybe. So we can see our m here is 2. So we will here have only two columns, right? For 1 and for m equal to 2. So for the second one. This is why our L tilde looks like this. So this is estimation using our principal components method. Then we can compute those. So 1 minus the squares of those. Let's go back again. So here you can see S11 minus sum of the squares. Right. So it's here given. This notation here means that it will square value and then, so it will square this, then sum with square this. Okay, and then 1, because 1 is our S11, so the diagonal. Okay, so this is how we get our specific variances. So those are our specific variances, and those are loadings for the first factor and for the second factor. Okay, and each of those loading is for one variable. So this is for our first, let's call it x1, okay, and our first factor, f1. Then second variable, but still first factor. So L21, L31, R41. Okay, in the first example it was simple because we had only L11, L21, and L31. Here we have two, so it is a little bit complicated still. Nothing special. So this is how we get our loadings matrix. Okay, and in the end it's easy to compute the residuals, so matrix of residuals. Okay, so when we just substitute this formula, so S minus our L, so this one, transpose, so this times this transpose plus this matrix. So this is what it says here. Oh, this is minus. Yeah, it's actually minus. It's mistake in the notes. So here it is not minus, okay? It's not plus, it's minus here. So it's mistake. Hopefully I will, before I upload it, I will fix it if I don't forget. Okay. Let's go back to Excel. So you can see that similarly you can apply other methods like this one. The estimation using principal components, even if you do with maximum likelihood. but maximum likelihood requires your assumption of normality. Okay, also before we go to the next example, we can always use a test, statistical test, okay, that we can test if actually two factors are enough to represent the covariance structure of this, our vector. Okay, so those tests can be developed, but we are not going into details, just for you to know. Okay, and in the end, we will mention something new here, factor scores. But let's first assume that we have more variables, okay, and see how we can choose that m. So here it was only one, here we had two, but let's see if we can choose that m actually somehow. Well, we can use the same method that we use for the principal components. So how we will choose m? First, what we want usually to do when we have huge difference between those values, we want to standardize. So what we need to standardize values, we need the mean of this variable, okay, mean of this, and we need standard deviations, right? But usually when we standardize, we use, instead of divided by n minus 1, so unbiased, we will use divided by n. Okay, what I mean is here, we don't use s, but we use p instead. Okay, so this is our averages. Okay, so our sample means are our sample standard deviations. And how do we standardize? Well, we subtract mean and divide by standard deviation. So this is standard deviation. And we do that for each value. So for example, for this 17, we know that it's fifth variable. We subtract from mean and standard deviation of the fifth variable. That is how we obtain the standardized matrix. Then what we do is obtain the covariance matrix of the standardized or the correlation matrix of the initial sample. So we always should get on diagonal 1, okay, in this case. And here we also divide by 50, notice that, because we here obtained standard deviation with p, that formula is divided by n, so by 50. So we need to use here divided by 50 as well. If you use here divided by 50 minus 1, then you would need to use it here as well. You would get different values. Okay, so next what we need to do is from, we already completed that multiple times, so you should know that. So next, what we need is eigenvalues, eigenvectors. Again, we use R, we get the eigenvalues, eigenvectors, and in this case, we will take the first 4. Okay, so now it's not as in principal components, but it's similar. Okay, still we need to explain as much as we can from initial, so to contain as much information as we can. Okay, so now there are a rule of thumbs that, for example, say to take all such eigenvalues that are not close to 0 or similar, or if we take of the sample covariance matrix of the initial sample, not the correlation, but covariance matrix of this, not covariance matrix of z, then we take all eigenvalues that are larger than 1, than unity. Okay, but because we standardized and took, then we will take all that are not close to 0, or they explain here like 98% of initial information. Okay, so we are taking only first 4. And then we also need the eigenvectors. This is also imported from R. And we will need later the eigenvectors in rows, not columns, to compute. So here we can write eigenvalues like this, so we can compute this line, okay, which suggests that so 4 is somewhere, or even 3 would be enough. So you can choose 3 or 4. Even if you choose 3, it would be okay, but because 3 and 4 are close, it's perhaps better to include both of those. Okay, But you can always, when you work in practice, you can always use multiple methods. Okay, and every method should give the same result. By method, I mean method of maximum likelihood or method of principal components, and they should give similar results. Okay, so we already draw this in principal components, those are our eigenvalues. Okay, then what we need is our matrix of loadings. Here we had only two, and we knew number priori. So researchers knew how many, let's say, how many factors are underlying. Here we chose 4, so we know that our matrix, so there are 4 factors, okay, so our matrix of factors, factor loadings, is going to be this matrix, okay, so 7, right, 7 times 4. Now, because we have eigenvalues and eigenvectors, we can just square root of our first and multiply with our eigenvector. So this is our first one. Square root of lambda 1 times our first vector, e1 hat. Okay. Same for the second one. So let's again. So what would be this number here? It's loading of what? Fourth variable on the first factor. Right. Our fourth variable is this. Let's say height or weight or anything. Okay. And that unobservable factor is first one. Or we can say weight of that variable on that factor. Loading or weight is similar word. And what we did not talk so far is the factor scores. So what we should first note here is that those factor scores differ depending on the method you use. So if you use the method of maximum likelihood, then you can obtain those factor scores, those numbers, a little bit differently. So you can imagine that those factor scores are actually some kind of estimation of those our unobservable variables. Okay, so we somehow put a number for that variable, even though it's unobservable. So basically what we do is we assume that those are our known factors, or let's say our known parameters, and then we estimate our f1, f2 to f4 in this case. Okay, so we estimate those values. We talked already about some methods of estimation, even in univariate statistics, like method of least squares, weighted least squares, method of maximum likelihood, or similar. So depending on what you use, you get different factor scores. Here we use principal components, method of principal components. So what we get is something similar to our ordinary least square estimator. Okay, for our f1 hat, f2 hat, f3 hat, in this case we will have f50 hat, so this here would be f50 hat. Okay, so we know in our ordinary least squared we obtain our estimates when we take, so if you remember, x transpose x to the power of -1, x transpose x, or y, because we used x and y, so y. Let me write this here. So it was x transposed x to the power of -1, then x transpose y. This is our ordinary square estimator, and we proved something about that one. But those are our factors as well, factor scores. So we obtain this for using this formula. But instead of x, okay, we put our L. So those are our known values now. And so instead of y, what would we put? What would be logical to put? Well, our vectors z. So those vectors, because we use those, so this vector here would be for our first factor. So how to obtain those four? So those for first four. So we can actually write this formula. This formula is written here. So, but using this matrix and the first column. Okay, but it is a column, not a vector, so we need to transpose this. Just follow this formula. I will leave it here. But you can look in the book as well, the suggested literature. But there is much faster way to obtain those. Okay, so there is, let's say, this formula that can be proven as well, but you get this matrix at once, so you get all those factor scores. Okay, so you need to transpose our lambda 4 by 4. So this is this selected matrix. On diagonal, you have lambda 1, lambda 2, lambda 3, and lambda 4. So that's just it, to the power of minus 1/2. Then A, in this case, A is this matrix Z. Let me put like this. So this is A, this matrix. Okay, and you can see it's 4 times 4, 4 times 7, 7 times 50, and you get 50 times. Yeah, you get 50 times 4. Because it's everything is transposed. With this first transpose, this is why. Because it's 4 times 50, and when you transpose everything, it's 50 times 4. And then we can extract some information from these factor scores with its same with the principal components, so you can like draw plots and see how do they behave, what are the values and similar. This is plot only of the first two, so those first two factors. Okay, so this is it for the factor analysis. Just keep in mind that this is just a brief introduction and there is much more to it. So this is just for your intuition, so you can upgrade your knowledge if you ever need to use it. So you know where to start and how you can start and what methods can you use and similar. Also keep in mind that it might be similar at first glance to the principal components, but it's not the same. It's different. The methodology is different. The variance of our x1s can be represented differently. Of our communities are similar. You can always read the suggested literature and come back with any questions that you have. So it would be nice if you want. Thank you and bye.